Hello everyone, let's have a discussion on diamond as a semiconductor. These are the contents of my presentation. First, there is an introduction about the topic. Next, there is a brief description about what is a semiconductor. Next slides contain information about why diamond as a semiconductor, properties of diamond and comparison of diamond with other semiconductor. This presentation also includes various methods of synthesis of artificial diamonds. Also, I would like to discuss about future perspective, application, conclusion and references. Next, introduction. Diamond is a promising material for cutting-edge control gadgets that offer low power utilization and high recurrence activity. High temperature activity with low spillage current is likewise expected due to its amazingly low characteristics, transporter focus and high implicit potential. Diamond has a high transfer portability, high breakdown field, a low dielectric consistent, and extremely high warm conductivity. Diamond-based control gadgets are relied upon to essentially lessen both conduction and exchanging misfortune. The high breakdown electric field, the raised versatility, and a remarkable warm conductivity make jewel a definite semiconductor for high power and high recurrence application. In low-doped jewel, they accept, for example, boron and benefit, for example, phosphorus. Doped molecules have low ionization rate because of high ionization vitality bringing about resistive material and thus high sequential obstruction for gadgets. So as to get down this issue, new gadgets idea must be proposed for the manufacture of high power electronic switches in view of precious stone material. Then, what is a semiconductor? A semiconductor is a material whose conductivity properties lies between conductor and insulator. Some examples are silicon, germanium, gallium arsenic, etc. There are two types of semiconductor material: extrinsic semiconductor and intrinsic semiconductor. Intrinsic semiconductor are pure semiconductor without any significant dopant species present. Extrinsic semiconductors are semiconductors that are doped with the specific impurities. Then, why diamond as a semiconductor? Compared to silicon, it can run hotter without degrading in performance. It is more easily cooled. It can tolerate high voltage before breaking down and electrons can move faster through them. Diamonds are capable of increasing power density as well as create faster, lighter and simpler devices. Diamond as a semiconductor outperform silicon by a factor of 23,000 times, gallium nitride by a factor of 120 times, silicon carbide by a factor of 40 times. As a result, diamond can rule higher power density application. Semiconductor technology roadmap for power electronic devices. This figure shows semiconductor technology roadmap. It is a critical for future diamond-based activity device to have a wafer size of at least 2 inches and defect density of 100 cm square or less. Various approaches to producing freestanding wafers from thick diamond films are being researched. A mosaic type method is now approaching 2-inch wafer size, but defect density must be reduced. According to Yole single crystal diamond wafer technology roadmap, low defect 2-inch wafers would be commercially available in 2016 to 2022. Then, properties of diamond. Diamond is one of the most extraordinary naturally existing material endowed with a variety of extreme physical properties that allow for a wide range of application, especially when all these properties are combined. Apart from the fact that diamond is the hardest material, which has led to its use in variety of mechanical applications. Its optical properties combined with its high thermal conductivity and a low coefficient of thermal expansion make it an excellent window material. While natural diamonds have these distinct characteristics, they are rarely found in the same stone. This variability and scarcity present too many challenges to the research scientists to give natural diamond any practical commercial viability for several applications along with semiconductor devices. Then saturation velocity. Saturation velocity rather than the mobility determine conductivity in high electric field. The production of optical phonons in crystalline lattice reduce the velocity of charge carriers at a high field. A high saturation velocity improves the performance of field effect transistors that operate at high frequencies. Next one is carrier lifetime. It is a critical when developing bipolar components. It is also important for devices that generate electron hole pairs as a result of radiation, such as radiation detectors. The recombination lifetime is less important for unipolar devices. However, a long carrier lifetime indicates low impurity and defect concentration and in thus important material quality indicator. Next one is dielectric breakdown field. A semiconductor material with a high electric breakdown field is beneficial for many devices. This is true not only for power devices like diodes and switching designed to block multiple kilowatts, but also for high frequency field effect transistors. The reason for this is that if a higher electric field can be tolerated, devices with a smaller dimension can be designed, resulting in faster switching. Intrinsic breakdown is a material property of semiconductor. It is caused by the impact ionization and avalanche breakdown. Extrinsic breakdown at defects on the other hand depend on crystalline quality and improve with a higher quality material. Diamond has the highest predicted breakdown field. Last one, thermal property. Diamond is the material with the greatest thermal conductivity of any non-material. Because of diamond's extremely high thermal conductivity, diamond-based devices can withstand high power level more easily. This happens because of the first stage of thermal management. Removing heating from source is facilitated by the device itself rather than an add-on solution. Next, comparison of diamond with the other semiconductor material. The capability of jewel can seen by contrasting its property with those of containing material for high recurrence and high power electronic gadget application. To be specific, gallium nitride and silicon carbide. The figure of legitimacy for precious stone inequality demonstrate the impact of their exceptional properties in comparison to other wideband hole material. Up until now, silicon has been considered a suitable semiconductor material for electronic gadgets. In any case, properties of the single gem precious stone created by the chemical vapor deposition strategy, when contrasted with those of silicon, clarify that it is a superior semiconductor material than silicon for electronic gadgets. They are as per the following table. Diamond has a much wider band gap than other semiconductor materials such as silicon oxide and gallium arsenide. It possesses some critical advantage including ability to handle higher voltage and power, high operating temperature, faster switching, better efficiency. Dielectric constant. A high dielectric constant is not necessarily desirable. Generally, substances with a high dielectric constant break down more easily. when subjected to intense electric field compared to material with a low dielectric constant. Next, electric breakdown field. High electric field is desirable. This is not true only for pure devices but also for high frequency field effect transistors. Electron mobility. High mobility is important because this means that electrons inside the material are able to travel at a high speed with a minimal scattering. This reduces the heat dissipation of any electronic device built from it. Next, hole mobility. Mobility is a very important parameter for semiconductor material. Almost always, higher mobility leads to better device performance with other things equal. Then, thermal conductivity. Diamond has a high thermal conductivity compared to other semiconductors, so it can handle high power more simply. Then, synthesis of artificial diamonds. First one, high pressure, high temperature method. The high pressure, high temperature approaches produces conditions for diamond developing that are similar to those found in nature. A growing cell that is equally pressured and filled with molten metal like iron, cobalt and nickel that has carbon atom dissolved in its used to generate tiny diamond seeds. Carbon atoms accumulate on the surface of the seed due to the high temperature of about 1300 to 1500 degrees Celsius and a high pressure of 5 to 5.5 GP. The image implicates the layout of common high pressure, high temperature process equipment. The belt press generated strong pressure. The pressure transmitting medium transmits a high load produced by the top and lower anvils to the growing cell. Due to the ring encircling this cell and restricting it in a radical direction, hydrostatic pressure is produced. The graphite is heated generate high temperatures. Anyway, electronic evaluation jewels can be created this procedure and subsequent precious stone are utilized for cutting and pounding. The next method is chemical vapor deposition. It is a technique for developing precious stone by making nature and the condition fundamentals for carbon iodide in a gas to choose a jewel substrate in precious stone crystalline structure. This technique for jewel development has been subjected of a lot of research since in the mid of 1980s, particularly because of its potential application in the semiconductor and precious stone diamond industry. Here a blend of carbon contains gas of instance methane and hydrogen are passed into the quartz tube at a weight of 0.05 atmosphere. Utilizing microwaves, the blend was warmed to 800 degrees Celsius, separating both the methane and hydrogen into the essential structure. The carbon is kept on substrate of the lens share a graphite. However, an extremely little extent as precious stone gem. The graphite is evacuated by the hydrogen, leaving films layer of jewel. Particularly because of its potential application in the semiconductor and precious stone diamond industry. Then, review of diamond power devices. Wide bandgap semiconductors have been used since several years to improve performance of power electronic converters. Materials such as silicon carbide or gallium nitride allow power converters to operate at a higher voltage, higher temperature and higher switching frequencies than silicon. These benefits are offered by the superiorities of wide bandgap materials. Among wide bandgap semiconductors, diamond is the most promising material for power electronic applications. Future perspective of diamond powered devices. The main challenges of diamond powered devices can be organized into 5 categories: material, devices, packaging, reliability, and integration. First one, material. The decrease in the defect and dislocation density, together with the enhancement of the interface quality, would also enable the reduction of leakage current and achieve BV levels closer to their theoretical prediction. The high cost of substrate is another crucial aspect to take into account for the commercialization of diamond powered devices. The next is devices. Technological progress in the wafer and processing quality will also have to focus on 4 key aspects related to device technology and performance. First, the development of vertical devices and a novel structure. Then, carrier lifetime control and device termination optimization, which could benefit from fabrication of multi-layer passivation based on high-K material, and last one, enhanced slew rate. In addition, the demonstration of high current diamond P-type field effect transistor and high current high voltage N-type field effect transistors would also lead to the smart integration of key components such as protection, drive, and possibility RC passive within the same chip. Vertical hydrogen terminated field effect transistors, depletion mode field effect transistors seems the most promising solution for high current voltage P-type device. The next is packaging. Packaging of diamond devices is an area where significant development will be required, in particular to accommodate the very high slew rates or the operation in harsh environment applications. It is therefore apparent that a unique packaging technique not compatible with those available for other wideband gap materials needs to be proposed. Then, reliability. As a further step towards commercialization, diamond devices will need to pass reliability tests, which can guarantee the device performance over specified time period and give an estimation of device lifetime in standard and harsh environment conditions. It is very likely that as the development of diamond-based devices progress, a dedicated standard and reliability test will be defined for diamond. The last one, integration. Wafer integration of parasitic and smart gate driving circuit will enable low volume diamond converters and improve DVDT and DLGT for the packaged devices. The smart integration of diamond and other wideband gap or ultra wideband semiconductor could represent one of the possible applications of diamond P-type field effect transistors in monolithic high-speed converters. Then applications. Diamond have for quite some time been utilized in machine devices, particularly while machining non-ferrous composites. While natural precious stone is still used for this, the size of manufactured jewels is more significant. The most common usage of diamond in cutting tools is done by distributing micrometer-sized diamond grains in a metal matrix, hardening it and then referred to in industry as PCD diamond. PCD tipped tools are often used in mining and in automotive aluminum cutting industry. The diamonds can detect redox reaction that cannot be ordinarily be studied, and in some cases degrade redox reactive organic contaminants in water supplies. This is because diamond is almost completely chemically inert and can be used as an electron under condition that would destroy traditional material. Diamond transistors are functional to high temperature and are resistant to chemical radioactive damage where silicon transistor fails. Diamond is used as potential radiation detection device. Next, conclusion. Diamond's remarkable benefit for power electronics have been accompanied by drawbacks and limiting factors. While some of these issues that have hampered the development of this material for years have been addressed, other questions remain unanswered. This topical review has provided no true overview of current state of the art and future trends, with the primary goal of reviewing diamond technology and modeling the most promising devices. Significant effort, particularly in last decade, has resulted in a new class of diamond powered devices that has the potential to find future place in the diverse power electronic market. When compared to commercial alternatives such as forged silicon carbide and gallium nitride, the comprehensive analysis conducted in this paper revealed that superior potential of diamond is primarily limited to high junction temperatures, about greater than 450 Kelvin, medium high frequency about greater than 20 kHz, and high voltage greater than 3 kV. Furthermore, the results demonstrated in this work have been highlighted significant thermal management issue that must be addressed in order to allow for the efficient parallelization of multiple diamond devices with a negative temperature coefficient. Then, future scope. Diamond is a promising material for next generation power electronics that require little power and operate at high frequencies because of its extremely low intrinsic carrier concentration and high built-in potential. High temperature operation with low leakage current is also expected. Moving on to the references from which the data is collected. Thank you for listening to the discussion on diamond as a semiconductor.